Hello everyone. Today in this lecture we will talk about absolute minimizing Lipschitz and definition of comparison with cons. Let's start with absolute minimizing Lipschitz. What is this? A function u which is continuous in u, and this u big is our domain, open and bounded. This u is absolutely minimizing Lipschitz on this domain u big, and we will write it u is AM Lipschitz in u. If Lipschitz u in V is equal to Lipschitz u in boundary of V. What is V? For all V which is compactly bounded in U. It means V is subset or subdomain of U such that V is bounded and closed. For example, if our U is our big domain U, for example, into D -1 to 1, V can be everything which belongs to this U, and also it is compact. 0.5, for example, should be compact. It means closed and bounded. Okay? How is it similar to Lipschitz extension problem? Actually, this problem is a strong version of Lipschitz extension problem. It was given f in the boundary of U. We have to find U which is continuous in whole domain such that U is absolute minimizing Lipschitz in U. And U is equal to F on the boundary. Absolute minimizing, it's not only in O1 just U, but in all sub domains of U should satisfy this this formula, because as we know that with name action wasn't the locality property wasn't on that case. Therefore, we have to solve absolute minimizing Lipschitz. And how we will solve? For it we define comparison with con. Okay, the definition of comparison with cone is simple. Let we have a cone with vertex x0, which is from Rn, and our cone has this formula: a plus b x minus x0. AB belongs to R. What does mean in 2D? For example, we have some x0 and AB. This is like formula of absolute value. Here A is height, like this one, height, and B is slope. Okay, this was definition of cone. Now definition of half cone or half line. For a cone C with vertex at x0, the half line is x0 plus t x minus x0, where t is greater or equal to 0. This is array, the array of C pass through X, like this. For example, we have x0, and here we have somewhere x. From this in x0, pass this row. Now let's prove this lemma. And this lemma says that if a set V contains two distinct points on the same ray of a cone C with slope B, then Lipschitz of this cone is equal to slope. The proof is easy. How we prove? Let's our cone is a plus b x minus x0, where ab is real. And we take two points on this line, x and y in Rn, and we find Lipschitz, cx minus cy divided by absolute value x minus y. We want to find Lipschitz. We know that formula of cx is a plus b x minus x0, and cy is a minus b y minus x0 divided by x minus y. So this will be absolute value of b times x minus x0 minus y minus x0 divided x minus y. Again, we use triangle inequality. We prove that is less or equal than b. Now we prove that the Lipschitz constant is absolute value of b if 2 points are in the line. So if now we have to prove that absolute value b is Lipschitz constant for c in any set. We take w and y, two distinct points on the array of c. Now we have y is equal to x0 plus alpha x star minus x0, and w is equal to x0 plus beta x star minus x0. Alpha beta is positive. What does it mean? Actually, now we are saying that now we have not array which pass through x, but any line pass through any x, like this. We have like this array, this is x0, or doesn't matter, maybe like this. Now we are proving that Lipschitz constant is the same. C x0 plus alpha x star minus x0 minus c x0 plus beta x star minus x0 divided by, just when we put, we get alpha x star minus x0 minus beta x star minus x0. So when we simplify, we get absolute value of beta times alpha x minus x0 x minus x0 divided by alpha minus beta and x star minus x0. So we proved that this is less or equal than b. So we proved that Lipschitz for any set y and w which belongs to V, Lipschitz of constant of this cone is equal to slope. Now corollary. Let V from Rn be non-empty, open set, and C cone with slope B. then Lipschitz C is equal to this slope. Therefore, if V is bounded and doesn't contain vertex of C, then Lipschitz C in the boundary is equal to V. What does it mean? For example, we have something like this domain, and we have several cones. Okay. Now, if we have cone which vertex is not in our domain, and the boundary satisfies, then it's everywhere. If this vertex is not in the domain, then Lipschitz on the boundary is also equal to slope. Okay, we will leave comparison with cone at the next lecture. Thank you.